Civil Engineering, BMS Institute of Technology. Hello. Can you hear my voice? Okay.
Yes, yes. Go
Good
ahead.
morning, one and all.
We can hear.
Good morning, one and all. I am Vinod Biar, Faculty, Department of Civil Engineering, BMS Institute of Technology and Management, Bengaluru. It is honor and privilege for us to have a eminent personality, Dr. Parthasarathy sir, with us for a technical talk. Thank you, sir, for joining us. Now I request HOD Civil to speak a few words.
Thanks, Vinod. First and foremost, I would like to thank Sir for gracing this occasion to deliver a technical talk in the time of COVID. I'd also like to express my gratitude to Vinod for organizing this. I'd like to inform my students the relevance of an industrial interaction. Now, whatever is being taught to you is something which is based on the curriculum of the university we are affiliated to. So the effort which Vinod is taking or Parthasarathy sir is taking is to ensure that you learn beyond curriculum and you learn things which are relevant to the industry, which are relevant to the modern world. So my heartfelt gratitude to all who are involved in this presentation. I'm sure it will be a great interactive session as well. Thank you, sir. Parthasarathy sir. Thank you, sir. Vinod, please continue. Thank you.
Thank you, sir. Now I request Yashaswini to introduce speaker of today's session. Yashaswini, please.
Good morning, everyone. I find immense pleasure in introducing our honorable guest, Dr. C R Parthasarathy, founder, chairman, and managing director, elected national executive member of Indian Geotechnical Society for the year 2016 to 2018. Dr. C R Parthasarathy is an industry veteran in the field of geotechnical engineering. He holds BE and ME degrees in civil geotechnical engineering from Bangalore University. He earned his PhD from Indian Institute of Science, Bangalore. He started his career as geotechnical engineer in 1993. He was involved in numerous site investigation studies at various levels for multi-story complexes, industrial buildings, bridges, water retaining structures, and various other things. Dr. C R Parthasarathy has undertaken pile drivability studies, jackup rig foundation investigations, and design. He was involved in the pile installation monitoring of several offshore platforms, involved in several jackup rig moves, and in addition, he has served as engineer for several geotechnical investigations. Dr. C R Parthasarathy is the founder director of Sarathy Geotechnical and Engineering Services Private Limited. The company, with its registered office at Bangalore, India, was established in 2008, provide both offshore and on-land integrated geotechnical engineering services in India and abroad. Since 2008, several consulting assignments were undertaken in the field ground improvement, pile foundation, marine and online geotechnical investigation, offshore foundation assessment, including jackup rigs and platforms. Apart from offshore pile monitoring, Dr. Sia Parthasarathy is instrumental in promoting quality testing of deep foundations in India. With this brief introduction, I would like to welcome Sir for the TED Talk.
Can you all see the screen?
Yes, sir. Yes,
Okay.
sir.
Yeah. Thank you. Thank you very much for a very elaborate introduction. At the outset, I thank the management of BMS Institute of Technology for giving me an opportunity to share some experience. Okay. The topic of today's presentation is soil compaction practices with some case studies. So I will explain to you maybe 3 case studies towards the end of this presentation. Before the case studies, I'll give you some perspective, probably give an insight how a compaction test has to be performed and what are the theory behind those compaction and so on and so forth. Before I jump into the presentation, for a couple of minutes, I'll try to give a brief introduction about our company. We have added some new services and products. Probably it will be of interest to many of you. So here is about the company. We started in 2007. Here's the vision and mission. We have a large depository of database across geography. Not only the geotechnical data, but also the foundation performance based on our testing measurements. So this gives us large database and the confidence to reevaluate the ground model for future projects, and thus we are able to provide this value engineering. And you can see here we are present in India and abroad as well, which have physical offices in Indonesia, and very soon Saudi we are going to start after this COVID. The primary focus was oil and gas sector, but of late we have also expanded our services to the domestic market, comprising of the real estate and infrastructure, railway, mining, renewable energy, and some part coming from the dams. Most of our services, more than 50%, is consumed outside the country, and thus the state and the central government have conferred export award consistently for several years. I'm sure we will be conferred with this honor even this year too. As far as the service is concerned, you could see here the geotechnical and geophysical investigation, drivability study, fatigue during driving, pile monitoring using pile driving analyzer, CAPAP analysis. These are all our core competence, leg penetration analysis for jack-up rigs, and the load transfer curve, the mud mat analysis, the shallow foundations, and all this will be a part of the engineering report while conducting the geotechnical investigation. We have several softwares, and the recent addition is Plaxis 3D to model complex three-dimensional soil structure interaction problems. In the domestic market, we also have these geophysical services, geological investigations wherever you encounter rocks to characterize the rock mass, arrive at the RQD, core recovery, rock mapping, etc. Geotechnical investigation with SPT analyzer. Probably I'll be not talking about this because of paucity of time. Design of shallow and deep foundation, bearing capacity, settlements. Okay. The green ones are all enable accredited, including the dynamic testing of piles. PDN, PIT is the pile integrity test, high strength dynamic test using pile driving analyzer. This is also another integrity methods, cross-hole sonic logging. Our laboratories enable accredited investigation and designs. Payment geotechnics. I'll give a brief introduction to this. Forensic in geotechnics, wherever there is a failure. For deep excavations, we provide complete solutions, and we have experience of executing this up to a vertical depth of about 18 meters in Bengaluru. As far as the, for the large scale infrastructure, currently the kind of investigation that we are adopting using mechanized methods, rotary methods, takes a very long time, over 3 to 4 days per borehole per locations, about 30-40 meters. So we have imported this from US, which is a multi-purpose high-end drilling rig, which can perform an SPT with an automatic hammer using this capstan. We can conduct a cone penetration test. It can drill into the coarse rocks material by wireline methods or the rotary methods. We have a very high power drill head, and 2 boreholes per day, around 40 meters, we are contemplating to complete, and thus we want to promote this to the large scale infrastructure projects. And this is going to be available in India for the first time, this model from end of October. As far as the deep foundation testing, conventional static load in terms of axial compression, pull out and lateral. These are all the integrity method, low strain integrity test. Cross-hole sonic logging test is also another integrity method. Thermal integrity profiler. Unfortunately, I'll be not talking about any of these things today. Shape is a qualitative shaft identification device, is the squid, and shape is the shaft area profile evaluators. These are very much useful for the quality control of the drill shafts. And finally, the high strength dynamic pile load test for evaluating the capacity of the pile by instrumenting the piles. Okay, with this brief introduction, let me jump into the topic of today's presentation. As you're all aware, Mother Earth is a very beautiful material. The natural soil you disturb, it loses its strength. Right? If you put some water and you compact it by some effort, it will increase its strength. If you put more water with more effort, the strength increases much higher. Again, it continues to do so until a certain point of time. There's the compactions I'm going to talk today. Okay. When you still again loosen the soil, you disturb the soil, it loses strength. Unlike any of the civil engineering material, this soil, Mother Earth, is a work hardening material, and it's beautiful to work with. Okay. Just to give a brief introduction to the geology of Karnataka. Okay, I was a part of a textbook that's going to come up maybe this year or early next year by one of the professor in Australia. So on soils of India. So we contributed a chapter from soils of Karnataka. Generally, the Karnataka soils consist of T categories. There is residual deposit, like what we encounter in Bangalore, Mysore, nearby in and around region. Then you have the black cotton soil that is towards the northern part of Karnataka, and it extends towards the Maharashtra and Andhra Pradesh, here, Gujarat, and so on and so forth. And finally, the shady or the lithomargic clays in the coastal belt of the state. Okay. Now, these residual soil deposits, like what we encounter in Bangalore, the overburden comprises of clay, clay sand, sandy clay, red muram, silty sand, silt. I think all of you are aware of this classification. Then you have the sheet rock, that is your granite, maybe it is gneiss, whatever, very hard bedrock. In between this overburden and the sheet rock, you have a refusal stratum, so it's a weathered rock or a disintegrated rock, okay, where the SPT N values are more than 50 or 100, and it's not bedrock either, so it's an intermediate stratum. So thus quantification of this material is very, very important for the foundations. As far as the compaction is concerned, any of these materials can be used to build an earth structure. Maybe it is a pavement, maybe an embankment. You can use this for backfilling, for reinforced earth walls, etc. So this is very important to characterize. So if you look at carefully the range of geotechnical parameters for these materials, example, the liquid limit, you can see the silty sand varies between 18 to 45, clay sand between this, okay, and clay silt is 50 to 60. Okay. Now the maximum dry density and optimum moisture content. So I'll talk about this in a minute. When you go to the northern part of the state, you encounter black cotton soils. These are all expansive clays. Okay, it swells in the ingress of moisture, particularly in the rainy season, and in the dry season it shrinks. Okay, repeated swelling and shrinking will undergo the volume changes in the soil mass. If you put up any structure, the lightly loaded structure, your pavements, your pipelines, etc., but these large deformations will undergo distress. So it will be very careful when handling any civil engineering or earth structure in these kind of problematic soils. So the properties of these expansive clays, the liquid limit you can look at is very high. No, minimum is 60%. It can go high to 80, maybe even 100% some of the soils. And the shrinkage limits is very low. So the very low shrinkage limit, very high liquid limit indicates there is going to be an excessive volume change in this material, and it's expansive. So we need to characterize properly whether the material is non-expansive or expansive. Perhaps if it is expansive, it is better to avoid this because, as I said, its volume change will make the structures undergo distress. In the coastal belt, lithomargic clays or shady soils, it's all lateritic materials, highly variable. You could see these all the lateritic material. Okay, and the classical case study that you can find in the public domain is a critical landslide. And every year after the monsoon, I think during the monsoon, you see the landslides happening across the Western Ghats. Okay, and you have to handle these materials very carefully. It also has a liquid limit of about 30 to 62, the maximum dry density of 15 to 22 kilonewton per meter cube, and the optimum moisture content 16 to 26. You see the CBR values. The soak values is very low, 1 to 9. So if you have a CBR of less than 5, I think you have a problem in building the or constructing the pavement. So you may have to resort for some remedial measures or ground improvement. Right. Now, any of these materials that is used for the earthen constructions requires compaction because you are disturbing the natural material and you are making it a more engineered material. So this compaction is employed in the construction of road bases, runways, earthen dams, embankments, reinforced earth walls, etc. And in some cases, the compaction may be used to prepare a level surface for building construction. So I'll be talking on one of the case studies how a low-lying area has been used with an external material as an engineered fill and then try to put the foundations, and what are the problems and challenges I'll discuss in that case study. And normally when you try to compact these soils, these are placed in layers, typically 75 to 450 millimeters. Generally, in our practice, I think around 300 millimeters is a leaf thickness, loosely filled, and then you roll it back to 200 millimeter thick and measure the density, whether it has achieved the requisite number. So each layer is compacted to a specified standard. I'll talk about the specifications using rollers, vibrators, or rammers, and any kind of compacting equipment. And thus, compaction is very, very important. So let us understand the basic definition of compaction. Although the test for compaction, the light energy, the high energy, or you call standard Proctor and modified Proctor, is codified in this IS code part 7 and part 8. I'm sure many of you or all of you have conducted this test in the laboratory. At first, compaction is a process that brings about an increase in soil density or unit weight, accompanied by a decrease in air volume. There is usually no change in the water content. Okay. Now, the degree of compaction is measured by the unit weight and dry unit weight, and depends on the water content and compacting efforts. So we'll discuss about this. That is the weight of hammer, number of impacts, and so on. For a given compactive effort, the maximum dry density weight occurs at an optimum moisture content. This is the process of a compaction curve, and let us examine that. So why do we do compaction? Compaction is done to improve the engineering properties of soils, like increasing the elastic stiffness, decrease the compressibility, therefore your settlements will be reduced. If you compact the soil, increase the strength, your bearing capacity will increase, decrease the hydraulic conductivity, so it can be used as a water retaining structure like your earthen dam, and decrease the void ratio, assist in maintaining the desired strength and stiffness, and decrease the erosion resistance, also particularly useful for the slope stability purpose. Okay. Now, how to do the compaction? I think all of you are familiar that you will do it with a compaction apparatus. This is a standard mold, Proctor mold, 1000 cc mold, or you can also compact with a larger mold, 2250 centimeter cube. Okay, generally, I think we do this for a soil which has a coarser aggregate. Probably we use this bigger material. Okay, there's two processes of compaction. One is the standard Proctor or the light energy, and the other one is the heavy energy or the modified Proctor. So let us see the difference between the standard Proctor and the modified Proctor, or the light energy and the heavy energy. So this is standard in the AASHTO ASTM IS code. Okay, it has a 2.5 kg hammer, okay, dropped at a height of 305 to 310 millimeter, 3 layers, 25 blows per layer. On the contrary, the modified Proctor or the high energy test will have a 4.5 kilograms of hammer at a 45 centimeter height of fall, and 5 layers, and 25 blows per layer. Okay. But if you use a bigger mold of 2250 to accommodate little big size material or coarse material, you drop 55 blows in 3 layers for a standard Proctor and 55 blows in 5 layers for a modified Proctor. So be careful. So sometimes we also seen that big molds are used, only 3 layers are impacted, and then the energy in this and energy in the bigger mold with 3 layers is not the same. To accommodate that volume, probably you may have to go for that kind of blows. This is all codified in IS code. So before performing any test, follow the IS code, read it thoroughly, understand what it says, okay, comply with the equipment and test procedures, know the objectives, conduct the experiments, record the readings, calculate, and then you develop the report. So one more very important aspect in how to compact it, I'll just explain in one trial. Assuming it is a standard Proctor test, you want to do 25 blows in 3 layers, right? So this, you know, the height of this mold, maybe around 12.7 centimeters. After compacting the third layer, you may have to have maybe around 5 to 6 millimeters only the soil compacted layer coming up, but you don't want it to be maybe around 15 centimeters, because the compactive effort into these compacted zones will get reduced. So mix the soil with maybe around 5 kilograms with some moisture content. Okay, you allow this moisture equilibration maybe for 24 hours. Then take some weight and put it on the mold. Then you compact it. So what is the sequence of compacting? First, you give a blow at the center, go to the north, east, south, west, do these 2-3 trials, and then continuously you can give the blows like this until you achieve that 25 blows. Now, once you have compacted this layer, very important how much weight you will choose for the second and the third layer. So you know what is the remaining height, okay, plus 6 millimeters. What is the weight of soil which you have already taken to compact a known height of the soil mass. Okay, then for a remaining height, you can calculate what is the weight required proportionate to 2. So half of that you put it in the mold, and then you give another 25 blows. Follow the same exercise for the third layer. So you find out what is the average height plus 6 millimeters. Okay, how much weight you require. Take that much of weight and then you compact it. So thereby, after compacting this third layer, you're ensuring that you will have only 6 millimeters of soils coming out of the mold. It cannot be more or it cannot be less as well. It has to be around 5-6 millimeters. Then you take a spatula, trim this material. Then you take the weight, either with the mold or extrude the soil and take only the soil weight. So you know the weight of the soil, you know the volume, so you know the bulk density. Take some moisture content, minimum 2 to get an average moisture content. Then if you have the moisture content, you know the bulk density, you can get your dry unit weight. Okay, I think this is how you have to do. So once you do that, then you get this point. That means you're getting the moisture content and you're getting the dry unit weight. Now you have to repeat this trial. So break the samples, pulverize it. Again, you add additional moisture content, mix it thoroughly. Okay, and then you continue the compaction in the same method I just described. So you get this point. Then again you break it, increase the moisture content, you get the third point. Likewise, you do this fourth point, fifth point. So what's happening here? So as you're increasing the moisture content, the dry unit weight is increasing, okay, up to this point. Further, any increase in the moisture content, the dry unit weight is decreasing. Right? So this maximum point at which your dry unit weight is the highest, we call it as the maximum dry density or dry unit weight, and corresponding moisture content is the optimum moisture content. Okay. Now, why there is an increase in the compaction curve, that is the rising limb with increase in the moisture content? This was first started in 1933 by Proctor. Several theories of compaction have been given, the lubrication theory. He said that initially when the soil has a very low moisture content, there is a capillary effect which has a very high resistance. Okay, and if you put some extra water, additional water, there will be lubrications, and these particles get reoriented. Thus, you get an increase in the density. Okay. Then further, Hojentogler, he gave a viscous theory. I'm not going to give very detailed because this itself is going to be a 2-hour lecture. Then come back in 1956, Hilf, capillary theory and the Poirier pressure. Lamb in 1960 gave a viscochemical theory. Why there is a rising limb in the compaction curve? Okay. Olson in 63 gave an effective stress theory. Barden and Sight gave the cluster theory. Podek and Laval the aggregate theory. And in IISc also, a lot of work on this has been done. Professor Murthy gave the cluster hypothesis. Probably in my master's, I extended this cluster hypothesis and tried to predict the compaction curve from the compression test. So I'm not going to talk about this now. The point is, on the rising limb of the compaction curve, there are several theories why there is an increase in the density with the increase in the moisture content. You can see mostly the lubrication would be one, and many other theories are there. Finally, the cluster hypothesis suggests that there is a lot of air voids, air pores, and the water pores during the compactive effort. The water pores exit into the air pores and not exiting out of the water, out of the soil. And thus, there is a repacking or the void, decrease in the void ratio and increasing the dry unit weight. So what happens beyond the optimum moisture content? Beyond the optimum moisture content, during a compactive effort, the pore pressures builds up, and thus you will get a very low density. So with this brief theory to the rising limb of the compaction curve and also the dropping limb beyond the optimum moisture content, what is important is you get a beautiful compaction curve. Okay, and this is for a standard compaction curve. This is a modified Proctor test. So what is the difference here? The energies are different. So the higher the energy, your optimum moisture content will be less, your dried unit weight will be higher. So please pay attention here. The higher the energy, the optimum moisture content is less, the dry unit weight is higher. So the y-axis is your dry unit weight, and this is your water content on the x-axis. Compaction curve is complete only when you draw this zero air void line. This is a saturation line. Okay, this is air voids is zero. Like that, you can have air voids of 2%, 3%, 5%, 8%, 10%. So some cases, the prescriptions is also that your air void line, if you drop this air void line here, it could be around 7%. Okay. Generally, the degree of saturation at this optimum moisture content will be around 88 to 93%. Okay, and this is a zero air void is 100% saturation line. Now, I just want to draw your attention also here. So you have different compaction curve. These are all light energy. Okay, now effort is same. Compaction effort is same, but the materials are different. Okay, you see, number one is liquid limit of 37, number two liquid limit of 45, 56, and 66. So what's happening here? As the liquid limit is increasing, your moisture content also is increasing. That is, your optimum moisture content is increasing. As your liquid limit is increasing, your optimum moisture content is increasing, your maximum dry density is decreasing. So you have 1.93, you have 1.8, you have 1.66, you have 1.45. Okay, so as the liquid limit increases, your optimum moisture content increases, your dry unit weight decreases. So that's where characterization of the material is very important, in these physical properties. Okay, these are all the index properties. Your liquid limit, plastic limit, very, very important, so that you can have some kind of correlations and evaluations. Now, with the same compactive effort, with the same same material, this is the same material, that is liquid limit of 38%, but there is a varied compactive effort. Okay, so you see 1, 2 is higher compactive effort, 3 is higher compactive effort, 4 is higher, still higher compactive efforts. So as the compactive effort increases, your optimum moisture content decreases and dry density increases. This is the same as your light energy and the modified energy, but in the same material, if the increase in the compactive effort, then this is the phenomenon. So you can choose what compactive effort you have to adopt when particularly using for the earth structures, right? Now, you may also be surprised, sometimes you do a compaction test, whatever we show that is a classical textbook curves, but many times you could see compaction curves of any of these order. Okay, so a liquid limit between maybe around 30 to 70%, this is a beautiful compaction curve. The kind of explanation just now we discussed, you will get this. For a very high liquid limit, more than 70-80%, you can get these two, and for a low liquid limit, less than 30%, and these two are possible here. The reason for these differences, there are literatures available who have given some descriptions, perhaps to do with the equilibration of the moisture content. So what happens when we put some moisture content? Okay, we mix it thoroughly, we tend to use the soil immediately after that, the compaction, then the moisture spread is not uniform, and thus For every moisture content, it is suggested that you equilibrate at least for a 12 hours period. So you mix it with water, put it in a polythene bag, put it in a desiccator, allow it for moisture equilibration. Okay, after 12 hours, then you remove the soil and then conduct a test. Probably you may avoid these kind of 1.5 peak or double peak materials, double peak trends. Okay. Now, with this brief introduction to the compaction test procedures, methodologies, and the theory, let us examine how it is used in the payments. Okay, as you all know, payment is a layered system to meet the following objectives. So it has to be strong to support the applied traffic load, to provide a smooth wearing surface, provide a skid resistance, and it should be durable, right? If you look at the structure of payment, it comprises of the surface course is a bitumen course, below that is a base course, sub-base course, and the subgrade. So what is relevant on the topic of this discussion will be the subgrade. This is a natural material, or it could be an subgrade by an external fill. Okay, so the strength of the subgrade materials is very, very important. That decides the thickness of these payments. So one of the parameter that is used in the payment design is the CBR, California bearing ratio. Although there are many other methods are available like resilient modulus, but the CBR is still widely used. The payments can undergo distress, excessive rutting, contamination, subgrade pumping, drainage problems. Okay, and you have the frost action, swelling, soils in expansive clays. Now, once in the season when ingress of moisture, the soil will swell and you see the undulations. So when we are driving a vehicle in a car about 100 kilometers, when you see this kind of bumps, it really hurts all of us, right? Although the payment compared to the any other civil engineering is very lightly loaded, but these are some of the aspects that is very, very important. Okay, you see the differential settlement, collapsing soils, liquefaction, and this is because of the slope failure. Okay, in an embankment. So why these failures will happen? These failures will happen because of the following reasons. Okay, most importantly, the inadequate observation and field control by qualified engineers and technicians during construction. So we take it for granted about the compaction. So we don't give much importance and supervise the work on the compaction itself to whether to ensure that material has achieved the requisite density for every layer. So I just discussed the lift thickness cannot be more than 300 millimeters, but we know many places we have seen in the highway embankment, railway embankment, they just come and dump with the tippers about a meter, maybe more, and then they do only a surface rolling. Thereby, it is only compacting the top 300 millimeters. What about the bottom? So the next layer will come, maybe another meter or so. Thereby, you will have strong layers for every layer only at the top 300 millimeters, but in between materials will be very weak. So I'll examine in the case study I'm going to describe in a couple of minutes. So the satisfactory payment performance depends on proper design and functioning of all the components of the payment. Most importantly is the material characteristics. So as I said, characterize the material. So for its index properties and its engineering properties, particularly the compaction characteristics, getting the maximum dry density, optimum moisture content. And thus, you develop what is the subgrade strength in terms of CBR. So how is this important? I already explained. The higher the CBR, the lesser is the thickness of the pavement. So my subgrade has to be very strong. It has to be well compacted. If it is not achieving the desired compaction or the degree of compaction, your CBR will be very less. That means your thickness is very high. But if your CBR is higher, your required thickness of the pavements will be much lesser. Okay. Now, subgrade soils can comprise of any of these materials. I already described in the Karnataka region, it can residual soils, black cotton soils, or shady soils, right? So, how to collect the samples? Collect the samples by borrowing a trial pits. We call as borrow material. You open a trial pit, collect some samples, bring it to the laboratory, and then you conduct a test. We just discussed this, how to do the compaction test and get the compaction curve. Right. So once your collected the sample, you have tested the sample, and it's ready. Now you use this material for constructions, for example, pavement construction or embankment construction. So how the compaction is done? Normally, it is done by the different type of compactors. You see here the smooth wheel roller, and the type of material that can be compacted with this smooth wheel roller will be crushed rock or gravelly sand. Usually, even the smooth wheel roller will be used for laying the base and the bitumen layer. All of you have seen during the construction of the pavements. Pneumatic tire rollers, sands, gravel, silty soils, clay soils is very popular now. Sometimes even these tires will be vibrated to induce more energy. Sheep foot rollers, which has the spikes in the drum, which is mostly for cohesive materials where it will have a kneading action. And in confined spaces, you use a rammer or a plate vibrator to compact it. So this is the smooth pull roller. You have steel drums, different weights that it has to be decided. And this is a pneumatic trial rollers. Okay, it has more tire at the back than in the front, and sometimes even these also can be vibrated. And this is the sheep foot rollers, which as it rotates, it provides a kneading actions, particularly useful for cohesive materials. It's well suited for clays. And in the confined spaces, you use the plate vibrators. So once you have compacted, you might have to test it. So what are the parameters to test for? So the target parameters are the relative compactions. So find out what is the density the material has achieved for that layer. And for that soil, if you have conducted a laboratory compaction, what is the maximum dry density? So this will give you the relative compaction or degree of compaction. Generally, it should be around 95% or higher. Okay. If the relative compaction is more than 105% possible, probably you may have to relook into the material that was used for the laboratory compaction and the material that is used for actual field practice. So this is a check and balance has to be made. The optimum moisture content working range will be plus or minus 1%. So when you have the optimum moisture, it can be 1% plus or 1%, 2% less or 2% more. So if you compact it much higher, say 5 to 8%, 5 to 6% on the wet of the optimum, that means it is more close to saturation. You will not achieve the requisite density, right? And thus the strength will be less. And so even with the dry of optimum, if you are compacting, you will not achieve the density. We will examine in the case study. So there is also an optimum air void tolerance of about plus or minus 1%. I explained the zero air void line. So like that, you can put 2% air void, 5% air void, 7% air void, 10% air void, and find out at optimum moisture content what is the air voids available, usually between 6 to 7%. So you can also allow that optimum air voids to be in the range of about plus or minus 1%. Okay. So for soils wetter than optimum, target the air void contents. That means where sometimes the expansive clays, for example, it will not be compacted at the optimum moisture content, perhaps slightly wet of optimum, maybe some 2-3% higher than the optimum moisture contents, so that you are actually controlling the swell potential. Okay, there you don't need to go with this range, but always work with the optimum air void tolerance. Okay, so with this criteria set, how to do a density test in the site? The simple thing is to drive the core cutters. So core cutters is a cylindrical piece. Again, it is only a 1000 centimeter cube volume with a dolly at the top. Okay, then you give a blows with the hammer. So you drive this. So we'll see the video of how to collect the samples using core cutters. Okay, and then you excavate around the soil, you pull this up, then you have the soil inside with a known volume, take the weight, take the moisture content, you get the bulk density, you know the moisture content, you get dry density. Dry density gamma D is equal to bulk density gamma T divided by 1 plus W. Right? I'm sure you would have done this in your laboratory experiments. And the other one is your sand replacement method. This is also IS code is available. Kindly go through this. This is all available in the public domain. Please read this. So the sand replacement method, so on a flat surface, you keep this open tray here, maybe to about 6 inches. You scoop the soils, collect in the tray to a gram. Don't waste that material. Okay, take the weight of that, take the moisture content. Then after that, you remove that plate and put this calibrating cylinder. Then you pour the sand, and you see how much sand is occupying that known volume here. So take the weight of the sand before pouring and after pouring, then you get the volume of that material, and thus your trade density. It's very simple. So these two are very widely used method to find out the in situ density, the core cutter and the sand replacement method. Although there are other methods to evaluate the in situ density, like your nuclear densometer, but since there's a radioactive element involved, it's not safe here. But these days, you have the digital non-nuclear density gauges. Honestly, I have not used those equipment still, but these are all very handy tools, I was told, to go and get your unit weight on the site. But conventionally, even today, the practice is to do the core cutters and the sand replacement methods. Suppose you have compacted maybe around 3 meters and your compaction quality control is not that much good. Okay. Later on, you see some cracks in the embankment or the compaction, or you want to ensure that the degree of compaction is achieved. No way when you miss the opportunity to collect the samples or test during the compaction layer by layer. After that, it will be again a very difficult task. Okay, if you want to really test it, then perhaps you do a boreholes, collect the samples in the boreholes, find out the unit weight, do a laboratory test, then you can compare the degree of compaction. You can also conduct an SPT continuously, maybe every half a meter. Okay, this is how the SPT is conducted. Okay, and this is a split spoon sampler, 63.5 kg weight, dropped at a free fall of 75 centimeters. Number of blows recorded for 3 consecutive 15 centimeter. The first 15 is treated as seating blow. The number of blows for the last 30 centimeters is treated as N value. Okay, and then you get the samples in the split spoon samplers. The moment you open that, please be attentive here. The samples split into half. It's not knife cut. It's actually naturally when you open this, it splits into half. This indicates the material is more towards cohesion less. Okay, it can be silty sand or sand, but if you don't see the samples breaking when you open this, okay, still in the cylindrical piece, it indicates it is cohesive materials. Okay, it's qualitative. Now you see the N values at continuously. Okay, in between you collect one undisturbed samples, and these are very low N values. The material is silty sand, so less than 5. I think it indicates a very loose soils. And this was a project where they put a very high-end villa, and those lightly loaded structures were distressed. And we examined what was the reason, and we could find out that the builder who graded the site excavated this silty sand in some other layer which was at a higher elevation. He just simply dumped it at a lower elevation without compacting it. And later on, when the villa was built, they put the foundations around 1.2 meters. You see that the around 2 meter thick of this unconsolidated material still exists below the foundations. So monsoon has come, the water has gone inside, and this starts settling. When this starts settling, all the columns, around 5 or 6 columns that was in this region started to experience large settlements, and thus the distress to the building. So that is very important even for the foundation, that the compaction has to be performed very accurately. And also you're conducting the field test, SPT can also get CBR values by direct correlations. Okay, this has to be calibrated for different materials, but correlation exists. This is another way of estimating the dynamic cone penetration test, DCP. This is not the conventional geotechnical DCP, but this is a lightweight DCP, dynamic cone penetration test. I will explain this procedure in the case study, but you can get the CBR values for different soils, have different correlations, and this is the penetration per blow in conducting the DCP test, and we'll examine how to do the test. The advantages, It can be operated by 1 or 2 people. Site access for testing is not a problem. Simple, rugged, continuous record of soil properties with depth, and can be used in pavement, course, holes, and suitably in many types of soils. And its demerits: does not obtain a sample. Obviously, it's a sounding test. Highly variable and uncertainty in gravelly soils, limited to only 1 meter, and extraction of cone can be difficult when you're retrieving after driving a meter. If it is very well compacted, it will be difficult. Now, with various methods, you have evaluated the density and find out the degree of compaction. Suppose you have around 100, say 1000 feet, around 300 meters length of compaction. You have evaluated at different elevation or different chain edges. You see, at this chain edge, your degree of compaction is high, corresponding moisture content is very low. This is optimum moisture content. Okay, this is what you have to achieve, 95%. Okay, when it comes here, you have not achieved 95% in this zone. The moisture content is very higher, implying there is a lesser moisture in this zone, there is more moisture in this zone. So all that you have to do is sprinkle a little bit more water here. Maybe perhaps you have to grade this and try to dry this area and re-roll it and recompact in trial that these data points collapse to these values. Then you are achieving the intended objective of the compaction. Okay, if you just let it go like that, probably when the pavement, the vehicle's movement is there, this zone where it is uncompacted, okay, the degree of compaction is very less, the pavement will undergo some distress at this point of time, at this location. Okay, let us get into the case study. Number 1, this was a part for the rehabilitation of the Bangalore International Airport. I acknowledge our colleagues who are all part of this project. This was to assess the properties of the substratum for the upcoming taxiway and also to assess the condition of the existing asphalt concrete on the runways and taxiways. And this was the scope of work. We did 2 deep boreholes for evaluating the bearing capacity, 9 trial pits, asphalt coating, the many DCP, the cone penetration test, and the laboratory test. I'll just show you some results of this project. So these are all the trial pits location. Okay, and 2 boreholes where they trying to build some structure here. They wanted some bearing capacity, and also these are all the pavement cores. Okay, may not be relevant for this topic. There was letting of the taxiways. Okay, and most of the problems is due to drainage. So if you are not taking care of the drainage, you have severe distress to those structures. And this was actually repaired. This was in Bangalore International Airport. 2 boreholes to 10 meters deep and trial pits 1.5 meters by 1.5 meters, around 9 numbers was examined. Okay, boreholes were drilled using the rotary drilling rig, and the trial pits are excavated to find out the in situ density of the material, so by driving core cutters. Okay. Now the DCP test was also conducted around 14 locations. The equipment consists of 16 millimeter steel rod to tempered steel cone with a 20 millimeter base diameter and a 60-point angle is attached to the bottom, and is driven into the soil by 8 kg hammer with a dropping height of 575 millimeter, and the process is repeated till the cone is driven to the required depth, usually a meter from the elevation. Okay, now you see this is a dynamic cone penetrometer DCP test. The cone at the base, and then this 8 kg weight is lifted around 575 millimeters and it is dropped, and number of blows is recorded as it penetrates. $43 blows, 44, 45, yeah, like that. So as it penetrates 1 meter, you can actually count the number of blows and record those continuously, and that's how you get the number of blows versus penetration. Okay. Now from this you get the CBR value there's some correlations as per the ASTM codes. The DCP is your penetration per blow. Okay, at every depth, you can evaluate the CBR versus depth. Now, this is how is plotted by the DCP test, and you have the lower bound and upper bound CBR values, and likewise for all the trial pits you conduct. So once you have taken the sample, you have conducted the DCP test. Perhaps they wanted to backfill that, and you see these trial pits. It was backfilled with the plate compactor. This is how is the plate compactor used, because the big rollers cannot come there because it's still a working airport. So the plate compactor was used to backfill those trial pits layer by layer, including until the surface is reached. Asphalt coring was also conducted, which was also part of the scopes, perhaps not relevant to this discussion. Okay, and this was also tested for its properties, indirect tensile strength, and etc. The samples collected in trial pits were tested for all these laboratory tests, most importantly the natural moisture content unit weight, modified Proctor test, because this is a airfield runway, and this California bearing ratio. Okay, and this was the test on the asphalt cores, indirect tensile strength. Perhaps I repeat, it is not relevant now. So in the two boreholes that was carried out, you see sandy silt in the top 3.5 meters, and then you have again silt continuing between 3.5 to 6.5, and finally below 6.5 the dense silty sand, and the other side the other boreholes has silty sand. Okay, this is a typical residual material that I already showed in Bangalore at the beginning of this presentation. As you can see, the N values are very high, 70 at the surface, maybe go deeper, it will be around 55, 40, 50, right? And these are silt materials. So when you open it, you see the split in the material also indicates this is more towards cohesion less. Okay. And the other boreholes, the N values are recorded here, and the stratification, silty sand, the second layer, the third layer, and so on. So I think these are all compacted material, perhaps before the construction of the airport itself. The borrow materials were brought from the nearby field, paddy field, and then they was compacted layer by layer, and it has thus achieved a very good degree of compaction. That's perhaps maybe more than 10 years now. And the cross-section profile of these two boreholes. Okay, I'll quickly go through this. Now, the trial pit samples were conducted for heavy compaction test. Okay, you see 1.78, 17%. Okay, 2.01, 11%. Okay, these are high liquid limit around 57, 56. Okay. And the other one is having a low liquid limit. These are all low liquid limit, around similar, around 30%. So as the liquid limit increases, your optimum moisture content increases, your dry unit weight decreases, and you see your lower liquid limit, you have lower optimum moisture content, higher unit weights. So this is in line with what we just discussed earlier. This is a typical compaction curve. And no compaction curve is complete until you put this zero air wide lines. So whenever you're presenting, please ensure that you have this zero air wide line. That is a saturation line. Okay. And now this is a CBR, soaked CBR and unsoaked CBRs. Normally, when you do a CBR value, penetration at 2.5% and 5%. So this should always be higher at 2.5%. Okay. If this is opposite is true, then probably you should repeat the test when the code says that. Okay. Soaked CBR is less than the unsoaked CBR, probably for the obvious reason. In the trial pit, you see the DCP test is conducted from 1 to 2 meters and 2 to 3 meters, and core cutter samples collected at 1 meter and at 2 meters. Okay, and here is the DCP value. There is the DCP value for this DCP test. Okay, and there is some circular from the US Aviation Department. Based on that guidelines, you see the recommended CBR, if it's 11, the modulus can be evaluated 1500 times that CBR values in PSI, and you convert that, you get 114. So if you get this modulus from the DCP test, you can also get the modulus of subgrade reaction, okay, with this formula. Okay, this is a given in Putri et al. 2012. Our boys were very happy. It was very tight schedule there, very restrictive region to go and do that test inside the airport. They were all very anxious and eager. Finally, very happy when we completed the project. Now, this is a very interesting second case study. Maybe I'll stop in another 5 minutes to 8 minutes time. This is for a villa project. Okay. What you can see here, these are all tall towers, which has about 2 basements. The excavated material, and this region is on higher elevations compared to this region. Okay. Now the excavated material from these tall towers, the client did not want to dispose it off, but they want to use it. So what they did was they excavated here and dumped it in this low-lying region and compacted it. Perhaps compacted it maybe around 2 meters to bring it to a certain elevation, ground level. And then they want to put this villa. All these things are individual villas, but they want to put the foundations on the top of this compacted. So usually if it is not an engineered fill, we never recommend the foundations to be on the fill. If you want to place foundations on a fill, it has to be an engineered fill. What is engineered fill? You conduct a thorough investigation and characterization of the material from the borrow site. In this case, it is here. Conduct a laboratory compaction test to evaluate your optimum moisture content and maximum dry density. And while compacting in this low-lying area, ensure that for every layer you are achieving 95% or higher degree of compaction at the placement moisture content. Then only it will achieve the objectives of compactions in improving the engineering properties of the soil. Otherwise, it is not. So when they did the compaction, they wanted to evaluate the ground characteristics, and thus these several boreholes were done because the compaction was around 2 meters thick, and then there was again the natural ground below that, so it drilled around 8 meters for each of these boreholes. Okay. This is the region of interest. Okay, when you zoom this, so these boreholes 1, 3, 5, 4, and 12 gave n values which are very, very low values, okay, compared to the rest of the site. And this is the zone we actually finally evaluated. So I'll talk about this borehole 1, 2, and 3 in just a few seconds. Okay. This is how the boreholes were drilled. Conventionally, using a rotary method, you conduct a standard penetration test. And we also conducted some dynamic cone penetration test. This is a geotechnical DCPT test, not the one we just saw in the previous case study. Okay, this will give you an equivalent N value by driving the cone 60 centimeter angle 10 centimeter square. A number of blows recorded for every 10 centimeters. Then you have some correlations. Up to 4 meters, you divide those values for 30 centimeter penetration, a number of blows by 1.5 and 1.75 below 4 to 9 meters, and thus you get an equivalent N. Now, when you get these DCPT values, you see these are all very low values, okay, and the SPT values are a little higher. She was only around 7. Okay, client was not convinced. They said that they have done compactions thoroughly. They have taken care, very nice, all quality control measures. And they alleged that your N values were wrong. And finally, the discussions going on for a few months. Okay, let us examine what's happening. So always when you go to the site, you get first-hand information. The site. So we visited the site and walked down all around the periphery. You see there's a lot of breaching of the soil, which was dumped. Okay, there was some piping action that's happened. And those boreholes 1, 2, and 3 I just marked in the last few slides. We went and took 3 samples. But before that, I asked them to share the photographs of the lift thickness, what they adopted. You could see here it is more than 300 millimeter. Sometimes the dumping of these Even you grade this, the lift thickness is more than half a meter. So I ask them, what is this lift thickness? Then they confess, no, this is only the worst layer. It was little higher, and after that, subsequently, we have taken all precautionary measures. Okay, now this is the cross-section borehole 1, 2, and 3. So we took samples at these 3 locations. So let us examine in borehole 2. This is the center part. Driving core cutters, you could observe the same dolly, the same size of core cutter. It is 10 centimeter diameter, 12.7 centimeter height. So it took around 30 blows. And this location is not able to drive it. It took around 30 blows. If you remove those 3-4 early loose blows, it's minimum of 25 blows it has taken to drive that core cutter at the center. Then we realized, very good, compaction is extremely good here, although the moisture content is very, very low. Perhaps they would have compacted it slightly higher effort with a low moisture content, and thus it is taking more blows, implying even if you conduct a strength test or a compressibility test, you will have a lesser compression and more strength at this location. Okay, on the contrary, we examined the trial pit close to this borehole 3 here. When you just poke this crowbar, it's almost about 8 inches. In the other side, it was hardly penetrating. Okay, but in the core cutter, you drive it only around 3 blows. It was driven. It was driven. So the same material, compaction is similar that as claimed by the client, and why this number of blows is taking only 3 here and 25 at the other locations. Now we come to the other end, borehole 1. Also, you draw this compaction, core cutter, hardly it took only 2 blows to drive. So if the compaction is uniform across that cross section, then how you can have a varied number of blows? This is also like a sounding test. The cylinder is the same. Okay, the penetration depth is the same. It's only hardly around 12 centimeters. Your weight of the rammer is the same, right? But it took 25 blows at the center location and just 2 or 3 blows at the other 2 edge locations. So based on this and all the informations, we demarcated that into 2 zones, zone 1 with fair compaction and zone 1 with poor compaction. And this it took 25 blows, the other 2 just took 2 or 3 blows. Okay, and the similar phenomenon was there on these things based on the N value. So we demarcated into 2 zones. Okay, and you see the compaction. So normally in the compaction curve, the placement moisture content and your dry density, whatever you have measured in the field, to be around this point, right? 95% dry density plus or minus 2% of our optimum moisture content. But what we actually measure, the placement moisture and dry density, is here. In this case, it is here. Okay, and in this case, it is still on the wet of optimum, and here it is too dry of optimum. Okay, so how it can achieve a uniform compaction across the site? And if you place footing on this varied compaction, so what will happen to the foundations? It will undergo large deformations at one locations compared to the other differential settlements, and perhaps after 1 or 2 rainy seasons, after constructions, all these things will come out. Okay, so even the samples that was taken, this was the poor zone and this is a good zone. Okay, you see the compressibility for a known pressure, it is very high compared to these 2. Okay, so with all these evaluations, we said that for a weak zone, N value of 7 is the minimum N value, and for a good zone, the N value of about 15 would be more appropriate for evaluation of bearing capacity. And we recommended the raft foundations for a 50 millimeters of settlements in zone 1, which has a fair compaction about 18 ton per meter square, and the other side which has poor compaction about 12 ton per meter square. Okay, if they can recompact it, this zone, they scrap it, put it by layer and achieve similar compaction to this fair zone, perhaps this allowable bearing pressure could be the same even in this case, because they are anyway making up. Okay, and the last one, This was also a foundation on an engineered fill. You see, these are the boreholes. There were 2 trial pits conducted, and DCPT test was also performed across the site to evaluate. And this was in Banashankari, where you had filled up region, but they want to put some quarters. This was a government project. So we asked them to excavate around 3 meters and then compact it on a controlled condition, engineered fill, and place the foundation as shallow as possible so that the stresses are within the compacted zone. And this is the site view. You see this material, I mean the soil had been graded, removed all the fill materials, and they brought this external material from some burrow location, and then they graded the site layer by layer compaction, and the engineered fill is completed. So we need to go and evaluate this engineered fill, although they had layer by layer quality control, but they wanted the third party verification. N values, you see the high N values in the compacted zone, 33, 19, 15, and below that is the weak N values. Okay, and in the other borehole also N values were very high, up to around 3 meters. Below that is a weak material. So if you place your foundation on top of this, your stress zone 2 times the width, maybe 1 meter width of foundations will be hardly within this zone. So we were very comfortable putting these foundations on top of this engineered fill because it has achieved the requisite degree of compaction. And so with the DCPT SPT test, you see the top layers were very well compacted, and you have the weak material below. In terms of the design N, 20 in the top 2 meters, and below that is all 9, although the stresses get distributed or dissipated within this compacted zone. Okay, even the DCPT results also suggested the same. And the compaction curve, and you see the placement moisture content that was evaluated is within this zone. So it also gave us confidence that it has achieved the requisite degree of compaction, 98% to 95%. Okay, it is 1.8 and 1.7776, around 16% of moisture content. Okay. Now, the shear strength measurement on the samples collected also gave a friction value of 35 degrees. With all this, the bearing capacity was recommended. Okay, and we recommended to put these foundations as shallow as possible. As you go deeper, the thickness of the compacted fill get reduced, and thus your allowable bearing pressure also get reduced. Okay, we asked them to put less than 1 meter because the stresses will be within the 2 times the width of the foundations and within the compacted zone. So then they constructed this building, 4 floors, perhaps now is 4-5 years, no challenge there, and the client has not come back. I think probably it has worked very well. So with this, I thank you for patient hearing. If you have any question, I'll be happy to address. Thank you very much.
Thank you, sir. Thank you, sir. Your talk was very informative and resourceful, sir. I'm sure student will appreciate it. Thank you, sir. Any questions, students? Any queries?
Yes, sir.
Yes, please go ahead.
Good morning, sir.
Yes, please.
Also, for light compaction and heavy compaction of a soil for different equipment, will the result be same or different, sir?
Different equipment means what?
Sir, the materials and all.
Yeah, definitely difference will be same. Yeah, the results will be different. See, suppose you take a red soil, okay, which is say clay sand, and you have a green soil, which is a silt, okay. The light compaction in a clay sand, red soil, and the light compaction in a green soil, that is silt, will have different values because their liquid limits are different, right? If the liquid limits are different, what will happen? So suppose red soil has a lower liquid limit and the silt, green soil, has a higher liquid limit. So which one will have more optimum moisture and less dry unit weight? I already explained, higher the liquid limit, more is the optimum moisture content and lesser is the dry unit weight, right? So these two are different materials characterized by their physical properties, basic index properties. So that is where classification test is as important to the compaction test, so that you can have these kind of correlations. That has already been verified. Many people have reported in the literatures. Did I answer your question?
Thank you, sir.
Any questions, students? Any queries?
Sir, good morning, sir.
Good morning.
For black cotton and red soil, we have soil classification as liquid and plastic limit tests, sir. Is
Right.
there any modern test like image analysis or artificial intelligence, sir?
I am not aware of that high-end technology yet. Perhaps people are working on it. I don't have that experience. I still work in the basic soil mechanics now.
Any questions, students? Anyone?
So,
Yes,
so
please.
for core cutter method or sand replacement method, is there any like they are the conventional method, right, sir? So is
Right.
there any method like any method using artificial intelligence or something like that?
See, artificial intelligence means you have to feed a lot of data and train those models, these machine learning models, right? I am not aware. That's why I said I don't have that experience of AI still. So actually, we have put up some research projects to work in our team. Perhaps maybe in next couple of years, we're going to come out with that. As it is, I am not aware of it.
Thank
Okay.
you, sir.
Thank you, sir. Thank you.
Thanks a lot, sir.
Thank you, sir.
Yeah.
Parthasarathy, sir.
Thank you.
So thank you for accepting our request. Sorry, I had to rush to a meeting. It just came. So we really look forward to this relationship. Fruitfully, I request Mr. Vinod to contact you. Maybe if we can have some kind of MOUs or internships, something which is a win-win situation, which can help you also and the students also. So with your permission, I'll request Mr. Vinod to coordinate with you, so if it's possible.
Oh yeah, sure.
Students for internship or any projects can be offered. Anything which can be within the limits.
We will discuss. We'll discuss. I think a couple of them raise a very important aspect, which is also our interest.
Yes, sir.
Unfortunately, I don't have experience. Probably I will put into the right team. So
Yes,
working
sir.
on it, and anybody is interested from your student side, we can have a collaborative project on that AI
Yes, sir,
and machine
definitely.
learning. Right?
Thank you, sir.
Yeah. Thank you. Thank you.
Sir, once again, I thanks to Akshata, ma'am. Thank you, ma'am. Thank you, sir. Thank you.
Thank you.
Thank you.
Thank you, sir.
Thank you, ma'am.
Thank
Thank
you,
you,
Anisha,
ma'am.
ma'am. Thank you.
Yeah, thank you.
Students, students,